This video is the first part in a series reviewing my dissertation, Results in Atmospheric Waves. Today we will talk about the first chapter, Leaky rigid lid tropospheric modes in a non-hydrostatic atmosphere. We begin by considering the layers of our atmosphere, of which there are many. However, our main concern lies with the troposphere, where all of our weather is contained, and the stratosphere, whose strong stratification acts as a barrier for atmospheric activity. We can observe this barrier in action in this flat top of a thundercloud, whose clouds for the most part bounce off this barrier. A classical assumption was to assume that all atmospheric waves would perfectly reflect off the stratosphere back down into the troposphere, acting as a perfect lid for the troposphere, hence the name rigid lid. However, this assumption is not perfect. The rigid lid assumes that the stratosphere to be a wall which stops everything. In reality, it is much closer to a steep ramp, which reflects much of a wave back, but allows some of it to leak out and stay in the stratosphere. This left diagram captures what happens quite well, with the incoming ray being transmitted into the stratosphere and the rest being reflected back. This diagram comes from the work of Chumakova et al., who devised the original leaky rigid lid boundary condition that depended on the stratification of the two layers, parametrized by the Brunt-Väisälä frequency n. Their work assumed a hydrostatic atmosphere, which means that there is no vertical acceleration. This comes from a classical scaling where the height of the atmosphere is far smaller than the horizontal scale of many weather events. For a visual, this horizontal line on that left diagram has a thickness and length that is in the same ballpark of this classical scaling. We take on a similar derivation as Chumakova et al., but our work is about what happens when the hydrostatic assumption is relaxed, which we do so from the start. We solve a similar equation in kinetic energy density, where x is a horizontal direction, z is the vertical direction, t is time, and n is that Brunt-Väisälä frequency from before. We scale the problem so that the top of the troposphere is at z equals 1. This gives a boundary condition that says that the function is differentiable across the two layers. Our new term in the equation that comes out is this term with the parameter delta, the aspect ratio of atmospheric height and length, where hydrostatic flow comes out from having delta be 0. Relaxing this singularly perturbs the problem. As a convenience, we can always rescale the problem so that delta is 1. To understand our results, we must first highlight the results of Chumakova, who finds the solutions to that equation are a family of baroclinic modes that decay in time by letting their energy leak out, counted out by integer m, and an exceptional decaying mode whose support is mostly near the stratosphere, which we call the stratospheric mode. By relaxing hydrostatic balance, we pick up a new barotropic mode that does not decay by this mechanism, and we dramatically affect the decay and frequency characteristics of the baroclinic waves. Here we see the structure of the solutions. First, we have our new barotropic mode, which while this quantity is linear in phi, does have a uniform horizontal wind, which comes out making it barotropic. Next, we have the stratospheric mode, which we see has most of its support near the stratosphere. Then our bottom row are the first two baroclinic modes, m equals 1 for 1 bump, m equals 2 for 2 bumps, and so on, which oscillate between the thicker sinusoids and the dashed curves when they leak into the stratosphere. Here we observe how the baroclinic modes behave in time as their horizontal scale changes. The frequency of a hydrostatic mode continues to increase as the length scale decreases, whereas the non-hydrostatic modes level off to match the frequency of the barotropic mode. The decay rates also increase in the hydrostatic mode, but they take on a non-monotonic character in a non-hydrostatic atmosphere, where it turns around to match the zero decay observed in the barotropic mode. This is where we turn the remainder of our attention to. Here we observe the decay rates of the first few baroclinic modes, where they generally follow a similar pattern. This similarity is not just a coincidence, but we observe that if we judiciously scale the horizontal scale and decay rates by m, that all of our modes line up to have the same pattern. And if we observe the x label, k over m, we can relate this to the angle of the wavefront, which emerges as this. This essentially tells us that there is a maximal decay rate of these modes that is relatively accurate for the waves that are not traveling at a steep or shallow angle. For the first mode, this decay comes out to about an hour of time, which is approximately the timescale of thunderstorms, which also operate at the non-hydrostatic height and length scales we started with. This has the potential to eventually make its way into forecast models in that it could tell us how long the particular features of a storm persist, which could in turn save lives. With that, I'd like to thank you for viewing this video. I will have more of these videos coming out in the coming days leading up to my exit seminar. If you like this video, then like this video and do the other social media things.